In today's topic, we will study the ionic strength effect on the rate of a chemical reaction. This effect was studied by the Lowry Bronsted and B. Jerem using the equation given by the D. by Huckel. This effect of the ionic strength on the rate of the chemical reaction was studied by keeping all other factors affecting the rate of the chemical reaction for a little or for some assumption at the constant. Here we are supposing that a substance is represented by the I. Activity of that substance is represented by the small letter A and I. So the concentration is represented by Ci here. So this equation or expression can be represented in this form. Okay, now we will talk about the equation that is obtained. This equation is shown here. Here in this equation, it is showing that the activity of a substance I is equal to the activity coefficient gamma I and concentration of a substance Ci. The equilibrium constant for the first part of the reaction can be shown here. So if we consider that here is a reaction taking place, first one giving this equation where the two substances named as A and B are reacting together. So these are getting converted into the complex form AB, and after some time where the irreversible reaction is taking place and we are using the K2 as the constant and Pe is the product obtained. If we want to know the activity of the substance A, we are showing it in the form small letter A and A capital, that is showing to the reactant name. So in the same form for the B, the activity of the B reactant is small a and B. So the complex form activity is in the form of A and this sign. After that, if we want to make the expression of a chemical reaction to determine the formation of the complex, so we can show this expression of the rate constant in the form of the activity. So in that case, we will give the equation in this form where we are writing the product or the complex on the numerator situation and the denominator are placed by the reactant activity signs. For example, the small letter A and small letter A with B and small letter A with A that are showing the activity of the reactant A and B. So if we want to show the expression of a chemical reaction exactly in the form of the reactants but not in the form of the activity constant, so we will show the reaction in this form. In this section we are showing that when the complex is taken above like represented by the AB, and here why are we using the activity constant, why we are using the activity coefficient as gamma. We are showing the activity constant or activity coefficient here because we are showing the exact quantity or exact value of the reactant complex, because we have come to know in the equation that the activity is equal to the activity coefficient multiplied by the concentration or the exact value of the reactant or complex. In the same menu, we are writing in the place of A, that is the activity, with the replacement of the coefficient of the rate of the reaction, and in the same way the exact value of the reactant complex. And downside, the A small a activity or the activity of the A is replaced by the reactant A and the activity coefficient of the reactant A, and the AB means that the activity coefficient of the reactant B multiplied by the reactant B is equal to the small ab. In simple words, we can say that when we are writing the A B, we will say that it is equal to the concentration B reactant with the gamma. Gamma is showing here the activity coefficient. Same goes for the reactant B, where we will say that small letter A and that is showing the activity of the reactant A. Here it will become the A, that is showing the concentration, exact concentration of the A, and the gamma is here as the activity coefficient. So in simple words, when we write the equation in this form, we obtain the equation that is equal to the K is equal to the AB mean complex multiplied by coefficient, activity coefficient divided by the reactants and with their separate coefficients. And if we want to determine the value of the complex, so we will take the complex on the left side and taken the denominator on the other side become the numerator, means that it's dividing on the one side and on the other side it will start multiplying. So we can show this in the other equation. As we know that this AB is kept here, so the coefficient present here will go to the other side, and as it is here in the multiplicative form, so in the other side it will become in the division form that is shown here in this equation. So by the overall concept we have get to know that the value, the concentration value, the molar concentration value of the complex AB is equal to this. It means that we have obtained the value of the complex in molar concentration. So if we know that a simple chemical reaction process in the second case, or in the case where the product is formed, so the rate of the formation of the product is equal to the K into AB and this sign. So if we want to know this value, by putting this we can solve this equation. When we have obtained the AB value, but when we put this equation in the main or major derived equation that is well known, so the rate of the product formation is equal to the K into AB equation that is obtained here. So the equation look like this. And here we go, whenever we study the kinetics of the such reaction, we compare these values with the simple chemical reaction as compared to the complex chemical reaction. In complex chemical reaction, we assume that the rate of the chemical reaction is taking place in which the reactant are reacting and making the complex, and this complex is getting converted into the product. But in the simple chemical reaction, we say that just the chemical reaction is taking place and just A and B react with each other after the K2, means that the reaction is going irreversible and it get converted into the product. In that case, if we want to show the expression of the reaction, we show the expression of the reaction in this form, where the rate of the formation of the product is equal to the K2 into molar concentration of the reactant A and molar concentration of the reactant B. After putting the value of the AB obtained, the equation appeared in this form. And when we make an expression for the general reaction where the formation of the product is this, when we compare these two equations, where on the left side both of the equations are representing the rate of the formation of the product, so both of these equations are comparable. When we compare, we obtain that here the K2 value is equal to these signs. Why? Because in the equation here it is written the molar concentration of the reactant A and B are cancelled out by, in this equation, the molar concentration of the reactant A and B. Only the things or the factors that are left behind to be studied are these. What are these? These are equal to the K2 is equal to the K small, K capital, coefficient of A reactant, coefficient of B reactant, and the coefficient of the complex. So, for a very dilute solution, if we suppose that the solution is very dilute, in that case we will consider that the activity coefficient of the species, means that the reactant A and B, we suppose it is equal to the 1, it is equal to the unity, and in case of the complex formed it is also equal to the 1. When we put the 1 in this equation, we will obtain the equation changed into in this form. When the equation is changed into this form, where we are writing the K2 naught. Why we are writing the K2 naught in place of the K2? We are writing the K2 naught in place of the K2 because we are showing here a special case, because that's why the K2 is replaced with the K2 naught. In that case, we have obtained that this small k and this capital K constant are replaceable by the K2 naught. In this equation, we will replace the K small and K capital with the K2 naught that is obtained in this special case. By putting these values, the equation appear in this form. So, where the K2 is a function of activity coefficient of a reactant as well as of that of the activated complex, whereas K2 naught is independent of the activity coefficient and it is the value of the rate constant at which activity coefficients of all the species are unity. It means that they are saying when we put the value unity for the activity coefficient of the reactant A, B and complex, then equation appear in this form. So when we know that the reaction or the procedure or the mathematical derivation is used or explained with the help of the Debye-Heckel limiting equation. Debye-Heckel limiting equation is written in this form. This equation shows that the log coefficient of the substance I is equal to the minus 0.51 zi square under root I over 1 plus under root I. What is the I representing here? I is representing the ideality of the solutes. Solute here means the reactants. How much the reactants are behaving ideal in the reaction process. If these are not going to react or act as the ideal, so okay, what we were talking about, we were saying that the I, capital I here is representing the ideality of the solute, means the reactants in this rate chemical reaction, because the rate of the chemical reaction is depending upon the concentration of the reactants as they are playing the major role, and if they are not behaving ideal, so it means that the Debye-Heckel limiting law is not capable to be applied. So it means that the ideality factors matters a lot. The reactants mean solute are acting according to the assumed things, because the ideality are the assumes matter. So if we come to know the equation, same equation, Debye-Heckel limiting law equation, as for the substance I, when we apply this equation to the substance A reactant, so the log coefficient of a substance A is equal to 0.51 ZA square under root I over 1 plus under root I. What is the factor ZA square? ZA square is a charge on the reactant A. Okay, so when we apply the same Debye-Heckel equation for the reactant B, the equation appear in this form. And if we apply the Debye-Heckel equation to the transition state, means the complex, then equation appear in this form. So when we obtained by comparing the two values, one was for the complex reaction in which the substance is reacting and getting converted into the complex form. Here we have obtained the equation appear to be in this form. As you know that if the values are same and signs are different, these values cancel each other's effect. So positive ZA square cancelled out by negative ZA square, positive ZB square cancelled out by negative ZA square. The left behind value is minus 2 ZA ZB. As you know, by multiplying the minus 0.51 multiplied by minus 2, it becomes plus 1.022. When you put this equation or value obtained after multiplying these two factors, the equation appear in this form. So the equation obtained here is called the Bronsted-Bjerrum equation, that is obtained with the help of the Debye-Heckel limiting law equations. So this equation shows that the rate of the chemical reaction is depending upon the ionic strength, that is Za and Zb. So if we determine the equation by assuming that I is to be very very small, that it can be neglected from the denominator as it is in the under root form, the value of I is further decreased, and as it is in the smaller quantity and present in the denominator form, by neglecting 1 plus under root I, the equation appear in this way. So this equation help us to determine the values by drawing the graph, so that we have come to know that it is a straight line equation, or it is a straight line graph. How? Where the y is equal to log k2, c mean intercept is equal to log k2 naught, and mx is equal to this, where m is representing to the slope and under root I is representing to the x mean x-axis value. Here in this passage we have to determine and clear some concepts that are very easy to be determined. Number one is that if we want to draw the graph between the y and x factor, that is the log k2 and under root I, we will get to know that here are the three forms of the graph that can be plotted. Number one is in the form when the reaction is taking place between the reaction that have the similar charges. It means that when the substance has a similar charges, means that these two substances will repel to each other, will have the repulsion forces among each other or between each other, and if we want to carry out the reaction, these repulsion must be reduced. In order to understand the ionic strength, ionic means strength means there are some ionic species surrounding to these reacting substances. There are some ionic species or charge carrying species surrounding to the reactant. It means that these ionic substances or charge carrying substances will decrease the repulsion forces between these two similar charges containing reactant, and in this way it will decrease the rate of repulsion between these two reactant, and hence it will result in the increase the rate of the chemical reaction, and so the graph obtained will show a straight line with the positive slope. Okay, what is the next point to understand? Next point to understand is that when the reactants are having opposite charges, means that when two reactants are having opposite charges, they will attract to each other, and the ionic species present, means we are studying the effect of the ionic species present surrounding to the reactant. So when the ionic species is present surrounding the reactants, they will cause decrease in the rate of attraction between these two opposite reactant. It means that the chances of rate of reaction will decrease because their force of attraction will be decreased by the presence of the ionic species. In this way the force of attraction between them decreases and result in the decrease of the rate of the reaction, and hence we will say that the slope will be obtained that will have the negative value. Let's talk about the third case. In the third case, when the reactant are neutral, these two reactants are having neutral appearance or are having neutral magnitude, means that there is no positive and negative charge and there is no similarity and opposition of the charges. So these are behaving as a neutral. When the charges are neutral or when the reactants are neutral and are having no charges upon it, in that case ionic strength will not play its role, because it was playing its role by decreasing the repulsion or by increasing the repulsion, by increasing the attraction or by decreasing the attraction. So as there are no charges, there is no repulsion, no attraction between these two reactants are getting react with each other by the presence of the pressure or some other factors. So in this way the ionic strength will not be able to play its role, and in this way the rate constant of the reaction are not affected by the presence of the ionic constants or ionic species. So as there are no electrostatic force, attraction, repulsion, the slope of the plot will be 0. Let's understand the slope, the three different kinds of the lines to be plotted on this graph. Okay, when we are talking about the reactants that have the similar charges, when we talk about the reactants that have the similar charges, in that case the ionic species or the ionic strength will play its role in decreasing the repulsion forces between these two factors, between these two reactants, and in this way by decreasing the repulsion between these two reactants will lead towards the increase in the rate of the reaction, and in this way we will obtain the graph in this way and the positive slope. So, when we talk a type of the chemical reaction in which the two reactant species are having opposite charges, In that scenario, what will happen? In that scenario, the opposite charges will have the attraction, and ionic strength or ionic species present surrounding to them will cause the decrease in the attraction forces and will result in the decrease in the rate of the reaction, so we will obtain a negative slope. So when we talk about the neutral species or nutrient reactant, in this way there is the zero slope. That was all about the ionic strength effect on the rate of a chemical reaction in solution phase.